Hello and welcome to another session in the Spark series. So, in this session, we'll look at why Spark is faster than MapReduce. We'll take an example and we'll see how MapReduce will process that application and then how Spark will process it. And then we'll know why Spark is faster than the MapReduce. Right? So, what we're going to look at is a word count. So a very famous example word count where you have the data. So this is your input data. As you can see, you have Hadoop, user, Scala, and yep, these are the words that you have and they are repeated. So this is the data that we have, and what we wanted to find out is we want to find how many repetitions are there for each word, like Hadoop, how many times it is occurring, or user, how many times it is occurring. So this is your word count example, right? So if you're working with in a MapReduce environment, if you want to process this using a MapReduce environment, there are 4 steps, right? The first thing that you have to do is you have to load the data. So once you load the data, the next thing that you want to do is you want to flatten this data. So you want to divide this data based on your space in this case, so that every element becomes separate. So you will get something like this. This is your flattening, right? Now once you flatten the data, what you have to do is to every element you just assign a key, right? You just give it as value 1. So Hadoop 1, user 1. So every element or every word you give it the value 1. And then what you do is you are going to group the data. So you group the data on key, so Hadoop, and then you make a sum of, like, Hadoop is occurring 3 times, user is occurring 3 times, Scala 5, and Spark 1. So this is the process of MapReduce. The same process we'll follow in Spark as well. Now what is the basic difference between these two, right? So in MapReduce, what happens when you load the data is loaded and it is saved in the hard disk. Then when you flatten the data, it flattens the data and the result is again stored in the hard disk. Then it assigns a key, it stores the data again in the hard disk. So every time you do a transformation, every time you're making changes to the program, the intermediate results are basically stored in the disk. So this is the main reason where the MapReduce is slow, because the input output reads operations is what it is causing it to be slow. So every time you have to do something, you have to read from the disk, again you have to write from the disk, right? So lot of overhead is there. So this is the problem with the MapReduce, right? So this is where Spark has made a small tweak. Spark handles this a little different, right? Spark will have in-memory processing. Before we understand this, how Spark is handling this, so we need to talk about RDDs. So once we understand what RDDs are, then we will come back and see how Spark handles this, right? So what is RDD? A resilient distributed data set. So RDD is a collection or immutable collection of objects. It is a read-only partition collection of records. So basically RDD basically represents the data across nodes in a cluster. So you create an RDD that will refer to a data set. So just like we read the data from a file and we give it a file handler in Scala. So similarly, when you read a data, or you can read that into an RDD. So RDD will refer to the data. Now using this, you can create more and more RDDs, like you can apply some filter conditions, then it will create another RDD. So it will refer to this data. So that's what your RDD is. So it represents the data across nodes in the cluster. Now there are 2 things that you can do with an RDD. One is your transformations. The other thing is your actions. Now transformations are functions that change the RDD data, and it will result in another RDD. For example, your first RDD is basically to load the data, right? So you have RDD which loads the data, and then on top of this RDD you can apply a filter condition. Maybe you just want to filter out the records using city, right? So you filter out that records. Now the result will again be another RDD. So this is about your transformations. So transformations are basically your functions that change the RDD data, and it will again result in another RDD. Now what are actions? Actions are functions that does not change the data but basically gives you the output. For example, count is an action. So what count does is it does not change your data. All it does is it counts the data and gives you the output. So that is your action. Transformations changes the data, it gives you another RDD. Actions basically gives you the final output. So these are the two basic things, right? Spark follows lazy evaluation. Now this is important to understand. This is where we are explaining how Spark is faster than your MapReduce. So Spark follows a lazy evaluation. Now this means that the transformations are executed and only check for syntax error, right? They are not checked for any other thing. We just look at the Spark just looks at the syntax. It does not store the data, it does not have any memory, it does not release any memory or give any memory. It basically checks your transformations syntax. Okay, they are not executed until an action is executed. This means no memory is allocated until the action is executed. So it will just check the syntax for the transformation, and while it does it, it will create a plan for the data flow. So how the data is flowing from RDD1 to RDD2 to RDD3, and then when you reach the action, it will start executing from action to RDD. Now since the plan is already created for each transformation, it will know which one to execute first, followed by which transformation or which action. So it has this plan. It does not need to store any data, it does not store any temporary data to the hard disk. All the processing is basically done in memory. So this is what we say as in-memory processing. So when the action is triggered, the plan is executed, and dynamically the memory will be allocated for each transformation and action. Now let's look back at our word count example and see how the Spark will process this. So this is your data. The syntax for this transformation is basically checked. If there is any syntax error, it will throw error and no memory is allocated. But at the same time, a plan will be created. No execution happens here. The next step is you're flattening the data, right? Again, the syntax for this transformation is checked. If there are any syntax error, it will throw the error. Again, no memory is allocated. A plan will again be created. No execution happens. So now you have loaded the data, you have flattened the data. So nothing has executed. It just creates a plan for this. Then we add 1 to the key. Again, a syntax is checked. If there is an error in the syntax, it will throw error. Otherwise, the plan will be created. No execution happens here. So this is your lazy evaluation. All this is happening because all of them are basically your transformations. They are just changing the data, right? Then comes your group by. So what group by does is it is going to give you the output. So this is an action. So here what Spark does is it will check the syntax, then a plan is created. So now you have the plan from step 1 to step 4, which is your loading the data to flattening, adding a key, and using a group by. So it has a full plan, right? And then because you have encountered the action, now the process will execute from step 1 to step 4. So it will load the data in the memory, and then it knows that it has to flatten the data. So the same memory will be used to flatten the data, and it will go all the way till your step 4. So nowhere it saves the data into your hard disk. It will do the in-memory processing. So thus it will eliminate those frequent IO hits. This is what makes Spark faster than MapReduce. The frequent IO hits, the input output hits in MapReduce slows down the process, while that is the tweak that Spark has done. Instead of frequently hitting the input output devices, it will do the in-memory process because it has the plan executed, and that's how your Spark becomes faster than your MapReduce. All right, so this is good. Now that we understand how the processing happens in Spark and in MapReduce, let's revisit the differences between these two, right? Just kind of a revision. So MapReduce follows a linear evaluation, goes from step 1 to step 4. And Spark on the other hand follows a lazy evaluation. It does not execute right from step one. It basically creates a plan. So MapReduce follows a top to bottom approach, that is the first step to all the final step. That's where it creates the execution. Spark basically follows from bottom to top approach. So it just checks for the syntax, and when the action is encountered, that's where it has this plan, and that's how your approach comes. From there, it will check for the plan and it will get executed. And MapReduce has a frequent IO hits because it does not have this execution plan created. So every time it has to save the data to the disk and then read the data from the disk. But in Spark, because the execution plan is created on the go, so this does not have to store the data in the hard disk. Rather, it can do a in-memory processing. And this is the main reason why Spark is much faster than your MapReduce. I hope you are able to understand how Spark is faster than MapReduce and what is the architecture of Spark and another thing. So again, these are things just for theory, and but we will start working in the practicals very soon. But a small theory here and there we will add it so that you understand the basics, you understand how things come out, and it is always good to know what we are dealing with before we start working on it, right? So that's all I have for this session, and I will see you guys in my next session. So, what are job stages and tasks? So, this is a very common interview question. So, this is more of a theoretical one where the interviews is basically checking or testing your understanding of the Hadoop system. So, let's understand what jobs are, what stages are, and what tasks are. So, at a very high level, a job is at the highest level of work in Hadoop. It basically represents a complete program that consists of MapReduce application. So, let's understand this. Let's break this down. Now, when you write a MapReduce application or a Spark application, so basically you will have a user here. So you would have a user, right? So this user or the developer will write some application. Now this application will, the code that he writes, this application will run on the data nodes, right? On the data nodes in Hadoop. And then obviously there is something called as map phase that goes, and then there is a reduce phase, and then finally you have the output, right? So this is basically the process. Obviously there is shuffling and other stuff that happens, but this is all the things that gets executed when you run this application. So basically you can say Spark Submit, right? So when you do a Spark Submit, basically these are all the things that gets executed, right? So this entire thing, right, is called as a job. So when you run a Spark Submit, it actually creates a Spark job, and then it executes all these things. It executes a map phase, reduce phase, and then finally it provides you the output. So this is basically a job. So when somebody is saying that they're triggering a job, they're basically doing the Spark Submit, right? Now this is at the highest level. Now within the job, there's something called as a stage, right? What is a stage? A stage is basically a logical phase of the job's execution. So this is basically a logical phase. Like you have something called as map phase, you have something called as reduce phase, right? So these are called as stages. Like this is a map stage, this is a reduce stage. So you have a job, and then you have stage. Within this you have a map stage. The in that map stage, what happens, right? Yeah, the mapper gets executed, and then in the reduce phase you'll have the reduce or the aggregation that gets executed. So it's just the logical separation, that is what is called as stage. So you have a job. Within the job you have stages. One is your map stage, one is your reduce stage, right? So you have this. Now, finally, what happens is like you have something called as task. So task is basically the smallest unit of work. So within the map phase or the reduce phase, there is some process that happens, right? Based on the use case, correct? So for example, if you are working if you are running an application where you're counting the number of words. So within the map phase, right, you will have to basically kind of split the data across, generate the key value pairs. So that is the some work that is happening. At the reduce phase, you kind of aggregate those count, right? So now who is responsible for carrying out all this task? That is basically the work of it. That is basically is what is called as a task. So that small piece of work is what we call as task. So again, you have job, then you have stages, and then you have task which does the actual work. So this is basically the overall structure. The job is at the highest level. Then the job contains stages, which is basically you have map stage and reduce phase, and then you need tasks, right? So this again contains tasks which actually carries the actual process. So this is basically what job stages and tasks are. What is shuffling, right? So shuffling is a process that occurs when the data is redistributed across different partition, that is nodes or workers in a cluster to perform certain transformations like a group by, reduce by, join, etc. Right? So this is the basic definition of a shuffling. So so basically what it means is that you have data in different nodes, right? In the cluster. So let's say you have a data in node 1, node 2, and node 3. Sometimes we need to transfer data from node 1 to node 2 or node 2 to node 3. So this movement of data is what is called as a shuffling. So why is it necessary? So let's understand with a simple example, right? So what I have right now is a simple use case where we have an input data. So this is, I can consider this as an input data, right? So my input, as you can see, I have certain words like mango, apples, grapes, right? Now, in a cluster, what happens is some of this data would reside in one node, some in another node. So if I consider this as my cluster, so this is my node 1, this is my node 2, this is my node 3, right? So let me represent this. So this is basically my node 1. So assuming that I have three nodes, this is my node 2 and this is my node 3. So basically this is my cluster. So this is my Spark cluster, right? This is my Hadoop cluster. Now, then what happens is that you have to bring, so this use case is basically to count the number of words, right? So how many number of apples are there, how many number of grapes are there, how many numbers of mangoes are there. So this is basically what happens in the map reduce architecture. So you have the data in different nodes. Now what happens is, right, here within each node, so what we do is we basically give it a number, like we convert this into key value pair. So key would be your mango number, and then value would be 1, right? Because this basically says mango, there is count 1, right? So this is basically our map phase. So in map phase we just assign a value, key values. So here the same data is just represented as key value. Now then, now look at this, right? So if I want to count number of mangoes, all I have to do is I have to see how many mangoes and just have to basically count how many values are there, right? For example, mango is 1, right? Here 1, there's another mango 1, so I should say 1 plus 1, so that is 2 mangoes here, and then 2 plus 1, 3 mangoes here. But the problem here is that my mangoes are in different nodes. So I have data mango here, I have another mango here, I have another mango here. So I cannot count it when we have data in different nodes. So we need to bring all mangoes together. Like here you can see we have all mangoes together, we have all apples together, we have all grapes together. So what we did is we basically brought mango from here, and this one here to this data node. Similarly, we did for the other fruits as well. So this transfer of data is what is called as shuffling. Okay, so this transfer of data is called as shuffling. And obviously this shuffling is required in this use case because we want to aggregate. So that is where we mentioned, right? So if you want to do transformations like a group by, a reduce by, or join, you need to bring the data from one node to the other node. So that process of bringing the data from one node to some other node is called as a shuffling. So shuffling may be necessary in some use cases. And now, is it a very good practice? It's not really good practice because shuffling basically means that you have a lot of overhead, right? Input output overhead. So it has some impact on your performance, but then there are cases like this where shuffling cannot be avoided. So this is one of the best practice that we do, right? So shuffling may be necessary in some cases, but cases where you can avoid shuffling, you have to do, or you have to reduce the number of shuffles so that your performance will be better. But this is basically the concept of shuffling. Alright, what is narrow transformation and what is wide transformation? So, what is the difference? So, very simple, a narrow transformation is a transformation that does not have any shuffle. So, shuffle is basically the movement of data from one machine to another machine in a cluster, right? So, if there is no shuffling, then we say it is a narrow transformation. So, narrow transformation has no shuffle, right? So there is no shuffle. So what are the examples? So we have transformations like, for example, filter, flat map. So here we don't need to move the data between multiple machines, right? You can just apply the filter. So those are basically the narrow transformations. Now, contrary, the wider transformations are the transformations that has shuffling. So examples like, you have the group by key. So in order to group, you need to bring all the uh, common keys together into a single machine, right? So again, another transformation, reduced by key. So you need to bring all the same keys into a single machine to actually do this aggregation. So this is basically the wider transformation. So narrow transformations do not require shuffle, and wider transformation requires shuffle. So that is the basic difference between a narrow transformation and a wider transformation. So that's it, and I'll see you guys in the next session. So what is cache and what is persist, and how are they different or how are they similar? So very important interview question, at the same time very important concept if you want to improve the performance of your Spark application. So let's understand what is cache and persist and how they are similar or how they are dissimilar, right? So basically, cache and persist are both used to store intermediate data frames or RDDs in memory. So basically, intermediate data in memory. Now, why? Because if there are certain, let's say there are certain piece of code that you keep executing, right? So there is a temporary data that gets formed, right? So if you want to reuse this data again, so you need to re-execute the same process and again, right? Instead, what you can do is you can persist the data frame, so or you can cache the data frame. So what happens is that data would get stored, that data frame is stored in the memory, and then you can use this or reuse this across multiple operations. So they help to avoid recomputing the RDD or data frames every time it is referenced. So with this, it will basically improve the performance. So for example, like I have a data frame where I'm basically reading it from a CSV file, right? So I'm reading it from a CSV file. Now what happens is, maybe I have to read this CSV file in some other line of code. Let's say at line 100, I again have to read this CSV. Then again, I would basically use the same one, right? I would again read the CSV. So what happens is that every time I read the CSVs, the same operations are getting performed unnecessarily. So what I can do is I could basically cache this, or I could basically persist this. Now this would be stored in the memory, right? So when I do this, this will be stored in the memory. Now instead of doing this, instead of reading this again, I could basically reuse this data frame. So instead of this, I could basically use this data frame because this is already cached. I don't have to reprocess. So that's the advantage of cache or persist. So it basically stores the data in memory so that you can reuse it. Okay, right? So that's what it is. But how are they different? So let's understand again how cache works and how the persist works. So basically, let's talk about cache first. So cache is basically a shorthand for persist, right? So now what happens in cache is that I talked about that the data frame is getting stored in memory, right? So in cache, that memory is basically your random access memory. So that data frame will be stored in memory, right? Now, like any other Spark operations, cache, when you call it, it does not immediately store this data. So this follows a lazy evaluation. So that's the great advantage of Spark, right? So only if you call, only if you use certain actions like count or collect or show, then only this thing will get executed. And then the data gets stored in the memory, right? So now the thing is this data is actually stored in the RAM. So if you have a bigger data to store, then it all depends on how big your RAM is, right? So if your RAM is very small and the data is big, maybe cache will not be able to support you in this. That case, we'll have to use persist. That we will see in a little while. But cache basically stores this data into the RAM, right? So advantages, obviously, since the data is stored in the random access memory, you can retrieve this much faster. So your operations will be all quick and it's very simple to use. All you have to say is data frame dot cache, right? So this is how simple it is to actually use this, right? Now, what are the disadvantages, right? We talked about disadvantages, but the disadvantages again, this stores in memory, right? So if the data is too big, then you cannot store this here. So it will not be able to make up that space. So that's the only thing. It will again, if your memory is like 4 GB and you're storing somewhere close to this, then it will degrade the performance. So that's the only disadvantage. But let's talk about persist, right? So persist is also something very similar to cache. Now, what we said, like, cache is a kind of shorthand to persist, right? So basically cache also stores the data frame. Now you can store this data frame in RAM, or you can also store this on disk. So that's the basic difference. In cache you can only store this data in the memory RAM, so that is why we call it as memory only. But here you can store this in the RAM, you can store this in the disk, you can also store them in both. So persist is a customizable storage level. It provides you the customized storage levels, right? So you can have something called as memory only. So memory only basically means, so these are the options that you can specify to the persist. So memory only stores this data frame or RDDs in memory. So this basically becomes cache. So when you use persist with memory, this is basically cache. You can also do memory and disk, right? So when you say memory and disk, basically what it is saying that it will store this in the memory, which is RAM, but then if there is more data, if there is insufficient RAM, then it will spill onto the disk, which is really good, right? So let's say you have a large data, so whatever the RAM can support, it will basically put the data into the RAM, and then the remaining data it will spill out into the disk, right? Then you also have something called as it also has another option called as memory only serve. So this basically means that the data, the RDD or the data frame is stored in a serialized file format. So we have multiple file formats, right? So this gets stored in the serialized file format. So serialized file formats, why? Because this will help in saving the space, right? Then there is also another option here which is called as a disk only. Right? So these are different options that you can use in the persist, right? So disk only, as the name specifies, this basically means that all the data you will be storing on the disk. You're not storing in the memory, but you're storing on the disk. So there is another option called as hop heap. So this basically stores in the memory, but it is actually stores of the Java heap. So you will need some extra configurations here. So this is actually using Java heap. Now, these are all the different memories or different options that we have. We have memory only, we have memory and disk, we have memory only, sir, which is serialization, disk only, off heap, right? So these are all the flexibility that the persist does. While in cache is just memory only. So that's a basic difference between cache and memory. So when do you use persist? When do you use cache? So if it is a simple use case where you just want to use where you want to store this data in memory, which is RAM, so you can go ahead with cache. But if you want more flexibility, right? If you want to store in memory at the same time, you also want to store in disk, or if you want to store in disk, or if you want to have the stored in a serialized format, if you wanted more flexibility, then we should go for persist, because you need to provide some configurations here. It's a very simple configurations, but this is where you will use persist. It gives you more control over how the data is stored when compared to the cache. Cache is just a memory, right? So that is where you have persist and cache. Okay, so now what are the advantages of persist, right? So the biggest advantage, as we see here, is that you have lot of custom storage levels, right? So you can store in different storage like memory, or you can store in disk. So that is a great advantage, right? Depending upon how the data is, you can choose your custom storage level. Now, because of this, it actually handles the large data, because not only you are able to store this data in memory, but you're also able to store the data in disk. So basically, that will handle large data set. Obviously, it provides serialization. We have seen one of the option here. So serialization, you can use a serialized storage to reduce the memory usage. So this is will be very helpful. Now, what are the disadvantages? We have seen all the advantages, right? So what are the disadvantages? So it could basically have a potentially slower access, right? Now, why is that so? Because if you store the data in disk, obviously retrieving this data will be a slower, right? So that is one of the, again, this is the trade-off you will have to make. If you want more flexibility, you'll have to definitely go with persist, right? So that is about cache and persist. So let's look at an example here, right? So I have this Spark. So I have this program written here, the Spark program. So we just basically, these are the basic configurations, we're creating Spark contest, Spark sessions and everything. Now I actually, here I have an RDD created. So now I have something, now I have cached it here. So basically this is how simple it is. So you basically say RDD or the data frame and dot cache. So this data gets cached here. Now I am just counting how many data is here. Now this will actually trigger. See, this is lazy evaluation, right? So even though you say RDD cache, it will not store the data immediately. What it does is it will basically form that logical plan, right? But when you call an action, in this case count, this is where it calls this already cache, and then the data will be cached. And I look at the persist as well. So same thing, I have a RDD persist. Now here I am giving a storage level. So here I am saying memory and disk. So what it means that store the data in memory. If the data is more than what you have in the memory, then you can spill it out to the disk. So that is the storage level. We are seeing different storage levels, right? This is one of the storage level. Again, I'm just doing a simple count. So I'm going to execute this. So very simple use case, nothing fancy about it. In the output as well, the count is 5 in both cases. The only thing that I'm showing you is how you can utilize this caching, right? So instead of this simple RDD, you could have a very big data frame where you are reading from multiple files, or you're reading from a very large data set. You could cache that in. And same thing you can do in persist. And instead of memory and this, you can use many other things as well, right? So you can also say like, hey, in this case, like I can say instead of I can say memory only here, and then there is also disk only. A lot of options as we have seen, right? So more customizable, right? So this is what we have. This is the cache and persist, the difference between them. So, and we have also seen an example. So let's try to understand this or you know revise this at the end. We look at some of the differences. Like I can put a cache here. It, let's put persist here. Then maybe what properties or aspects that we are looking at. Just a simple line. Okay. Okay, so let's look at the default behavior here. So what is the default behavior of cache? What is the default behavior of the persist? So it stores the RDD or the data frame in memory, right? So this is only memory only. So this is the different sorry, this is the default behavior, right? But over in persist, you have different storage levels. So you can store it in memory, you can store it in disk, right? You can store it in both cases, right? So that's the one. Storage again, if we talked about storage levels, this is just memory only, but this is like you have different storage levels like memory and disk only, and so on. Now usage, if I talk about usage, simple use case, when if whatever the data that you want to store it that it fits into the memory, then yes, you can use this. But if you want more flexibility, let's say if you want to store the data in serialized format, or if you want to store this data, or if you want to persist the data in memory and disk, or just disk, these are the things you can use using the persist. Okay. And if I look at serialization, so this does not support serialization, but this supports serialization, all right? And if I look at performance, right? How does this perform? So if it fits within the memory, this is super fast. This is really good performance, fast access if it fits into the memory. Here, because we have multiple cases like a disk, we have the other serialized formats, and so this performance might be a little slow if we use this kind of stuff. But other, if you use just a memory only, this will basically work very similar to the cache. And again, that data should fit within the memory, otherwise it will be a little slower. So this is basically the difference between cache and persist. The advantage, we have seen the advantages, we have seen the disadvantages, we have seen the difference, we have seen an example, we have seen when to use, when not to use. So basically both cache and persist are really important. You need to use this. You will be using this in your applications if you want to reuse the same data across different places. So this cache and persist will help you store this data, and then you can reuse this data across different places. So I hope this was helpful, and I'll see you guys in the another video. Specifying schema using strut. So how do you specify a schema using something called as strut? So for example, let's look at this file, right? So this file contains the data. It contains something called as invoice, customer ID details, age, category, quantity, price, and payment method, right? So if I'm reading this data, and if I want to define a structure, so basically a schema, right? Saying that, hey, this invoice number should be just an integer and it should not be null, or it should have something something. Same thing with age, it should not have a null, or it should be just an integer. So this is basically we are saying we are defining a schema, right? So how do you define a schema for a data frame using struct? So struct is one of the ways how you can define a schema. There are other ways as well, like case, but this is one of the ways, and this is sometimes asked in the interview question. So usually, like in most projects, you do not use it, but this has come across multiple interviews, so I thought of covering this here. So let's look at this right now. Struct basically contains something called as struct fields. So we have something called as struct field. Right? So let me just write it down nicely. So we have something called as struct field. All right. So struct field, it basically defines each column in a data frame. So it defines columns in the data frame. Okay. Now what it defines its name, it defines the data type, it tells you whether this has contains null, basically a schema, right? This is what you call in database like schema, right? So struct field will define each struct field will define all these things for each column, and this collection of the struct fields is what we called as a struct type, right? So this collection of this struct fields is basically what we called as a struct type, right? So this is what struct field and struct type are. So now what we'll do is we'll look at an example. So we'll look at reading this file that we have just seen, and now how the struct type or struct fields are defined, right? So this is basically the Spark job or the Spark code that I have written. So now here, what I'm doing here is I'm defining a schema. So I have struct fields. So again, struct fields are basically defines columns, right? So here I'm defining invoice number. I'm saying it is an integer type. I'm saying nullable equal to true, which means this can be null. I'm doing for customer ID. I am defining it as string type, which basically customer ID is a string, and again, it is nullable. Age, I'm defining as integer type, category string, price, I'm defining it as double type, payment string type. All of this are nullable. Then what I'm doing is I am basically reading this data frame, right? So I'm saying this header is true, and here I'm applying the schema, right? So if you see here, right, schema, this is a schema that we have defined. So we are saying, hey, I have defined a schema using struct here, and I am passing that schema over here, enforcing that schema here. Now this data, the whatever data that we have, this data will be enforced by this schema. This schema will be enforced in that data, right? And then I'm basically showing this data, right? So this is how you can create a struct type or struct field schema for your data, and then you can basically, you know, you can basically show this data. Now, if you want to refer to any of the columns, you can use this column names here, right? So that is basically how you use struct type. In some cases, I've seen people use it, but most preferably is a case class. But this is also something which has been asked in the interview question, so I thought of covering it. Okay, so we have a use case here. Basically, the interview will come up with something like, say, I have a data something like this, right? So you may not have the heading here, but he will say like, hey, I have something data like this. Now I want you to infer the schema. So what does that mean, right? So in Spark, schema inference basically refers to automatically detecting the structure and data types of the columns, right, in the data set. So now you can create a schema using struct type or case class, and then you can assign the schema to here. So basically structure, but then if you want to automatically detect the schema. So sometimes what happens is you will have a data set which has like 200 columns or 300 columns. So it might be difficult for you to actually create a case class or structure for those 300 columns. So in those cases, what we usually do is we basically use a concept of schema inference. So schema inference, basically what it does is it will scan this data. It will basically look at this data, right, each column by column, and see what kind of data is there. And based on that, it will automatically detect the data type, and it will kind of automatically provide or give a schema to it. Explicit. Now here we are not explicitly defining a schema, rather we are depending on the Spark to scan this data and come up with a structure for it. So that is basically a schema reference inference. So this is very quick if you don't want to write the schema. But then sometimes what happens is you should be careful with this, because sometimes what happens is if you get, for example, if you get files every day, so file one may have data in one schema, then it would have created the schema based on this file one. But if your file two is actually different, then it will create problems for you in the downstream. So that's where, if you know the data, then you should go for creating a schema explicitly. But if you're not sure of the data, or if no, if it is like huge, then yeah, you can definitely use the info scheme. And I've seen many projects using this info scheme, especially when you have like 200 or 300 columns. So it's very difficult, right? So what I'm going to do here is, here's an example. So you can see here, this is simple Spark statement, Spark read dot option, where the reader is true. I'm reading the CSV file and I'm providing an option. So this is what it is, right? Infer schema. So infer schema to true. This basically tells Spark, hey, you know what? I don't have a schema yet. You could go and scan this data. Based on this, you can create a structure and define the schema accordingly. So that's what infer schema is. So this is a very small file, and very little data is there, so it will not have any problems. In most cases, even if it's a big file, you won't have much problems, because most of the time, right, what happens is that the data that is provided is fine. And usually the schemas do not change. Like if they send IDs, just numbers in one file, and the next file they don't send in characters, right? So that does not happen. If that happens, then you will have to get in touch with the business team. But anyways, this is what the schema inference means. It will automatically scan the data and create a schema, the Spark. So you can see here, this is a schema that it has created. Pretty good, right? Invoice number is integer, which is correct, because all my invoices are in integer. Customer ID is string. Age is again integer. Category string. Quantity is integer. It should be integer. Price is double, right? Because in some cases, I have like 100.2 or 3, something like that. Payment methods again string. So it is accurate. It has provided me the details. So you can use this whenever you don't have a schema explicitly. If there is too much of columns, yes, this is very, very helpful, right? So this is what the schema inference is all about. What is a broadcast variable in Spark? Okay. So broadcast variables in Spark are a mechanism for efficiently sharing large read-only data across all the worker nodes in a cluster. So let's understand this. So let's break this up in a simple way, right? So let's say in a cluster you have many nodes, right? So for example, you have these many nodes. Now each node may have to do some sort of a joins or some sort of operation. So let's take an example where each node, this node, we have to look up into some large data set. So what we have to do in that time, if this node has to use that data frame or the data set, so this is the data set. Now we have to transfer this data set here, right? So similarly, this may also require this. So we have to transfer this data set here. Now, this transferring of the data set will cost us operations, right? It will cost us, it will increase this, it will decrease the performance of the code, right? So, because every time you're transferring their input, output, overhead, all the certs. So now, instead of this, what you can do is you can do what is called as broadcast. So what broadcast means is that this large data set, this we will create a cache and place it in each of these data nodes. So you will have a cache of this data set here, right? So it will only be read only. So this cache now instead of sending this data set here, the data is already there within that node. So now all the operation they can reference it from here. So This will be very useful and your performance will be much better, right? So now question, when do we use this broadcast, right? So we use when we have large lookup tables, right? So instead of transferring the data, which is static, we will basically broadcast this data. For configuration settings, you have configuration data that needs to be shared. Sometimes, there might be some configurations that we need to do for this program, and that can be broadcasted as well. Again, static reference data, anything that's just static, which needs to be utilized for joins or lookups, whatever it is, you can broadcast it. So we'll look at an example how we can do this broadcasting. So here I have created a read-only data set, which is the lookup table, which we'll use as a lookup table. So this is a data set or that we are going to broadcast. So simple map where we have key value pairs at Alice 1, Bob 2, Catherine 3. This is a very small data set, but in real time you have to actually use a bigger data sets to actually make sense, right? So we create a broadcast variable. So this is how you create a broadcast variable. So you put spark dots proc contest dot broadcast, and then you pass on the table that you want to broadcast, right? Then we are creating an RTD here. And now, how do you use your broadcast variable, right? Here we are using the broadcast variable to get the value, right? So here we are saying broadcast where value of this name. So here name we are trying to map it. So we are basically using as a lookup here. So this is basically how you can broadcast. This is a code for this broadcast, and if you run this, it will run and it will basically give you the output for this, right? So this is what broadcast does. And again, there are scenarios where you can use a broadcast when you have a large data set, and instead of transferring this data set again and again, you can basically broadcast this. So that is all about broadcast. I hope this was. What is the difference between map and flat map? So map and flat map of transformations operations which are used on your RDDs or data frames. So what does map do and what does the flat map does? So let's start with map, right? So what map does is the map function transforms each element of an RDD or data frame into a new element by passing a specific function to it. So for example, you have a data frame which you have, let's say a data frame has some data, let's say numbers like this 1 2 3 4, right? Now what map does is, if you are using map, so what map does is it passes for each of this element, it basically passes a function. Look, for example, you are trying to do a square of this number. So now what map does is the square of function will be gone to every element. So it will be 1 square, then you have 2 square, then you have 3 square, then you have 4 square. So the output will be here. The output of this like 1, 4, 9, 16, right? So this is what map does. So if you observe here, the input we have 4 elements, the output also we have 4 elements. So map basically applies the function to each element. The same input number of elements will be same. If you have 4 input elements, you will have 4 output elements, right? So this is what a map does. Contrary, on the other hand, flat map. So if you have, let's say you have 10 numbers or 10 elements, it's not guaranteed that you will have the same number of elements coming as output. So that is basically your flat map. So the output can have any number of elements compared to the input, because each element can be mapped to 0 or more output elements, right? So A flat map can produce multiple output elements for each input element. So it also transforms the data. Similar to map, flat map also transforms the data, but the difference is that you can have more than one output for each element. Okay, so map is a one-to-one relationship between the input and output, whereas flat map has one-to-many relationships. So if this is a basic difference. So let's also look at an example here. Here we are reading the Spark application, and we have a RDD here. So basically, five elements, one, two, three, four, five. And here, what we are trying to do is we are passing the map, we are calling the map, and here we are passing a function. So the function is basically num into num. Basically, what we are doing is we are squaring the elements. So one each element, it will be multiplied by itself, like 1 into 1, 2 into 2, 3 into 3, 4 into 4, and 5 into 5. And then we are printing this, right? So that is what map is. Flat map here, we have this statement, or we have a certain sentences. We have three sentences right here, strings. And what we are doing is we are adding a flat map. So this is a function that we are passing it. So we are splitting it. So now hello world, it gets split. Apache Spark is great, it gets split. Flat map versus map, it will get split, and then we are printing it. So observe that here we have five elements, so your output will also be five, but here the output will be different. Number of elements will differ. So that's a basic difference. So if I execute this here, I should show you the, let's see, the output, right? So this is the output of the map. So you can see here, we are squaring the number 1, 4, 9, 16, 25. That's a square of 1, 2, 3, 4, 5 respectively, right? And you can see the flat map here, right? So flat map, hello world, it's split into hello and world. Apache Spark grid again is split into different. So you can see the number of elements that we passed here was three, but then here we ended up having more than three elements. So that is basically the one to many relationship that I talked about. So this is a basic difference of map and flat map. Map, you do one to one relationship. Flat map, you can do a one to many relationship, right? So that's all about flat map and flat map. I hope this was helpful to you guys, and I'll see you guys again in the next session. What is a catalyst optimizer? So this is one of the favorite interview questions. So if you are a highly experienced person, let's say you have 10 years experience, 15 years experience, this is definitely one of the questions that you can expect. Okay, so very important concept. So what exactly is a catalyst optimizer, right? So at Catalyst is Spark's SQL internal optimization framework that converts an SQL data frame queries into highly efficient execution plans, right? Using rule-based and cost optimization, right? So this is the important thing. So highly efficient execution plans. Okay. So this is basically the definition. So now let's understand this with a simple example, right? We need to understand this a little bit more in detail. So let's take an example. Let's suppose that you are working at an Amazon, right? And you deal with a lot of data there, right? So let's say you have a table where they are storing details of the customer, what they have purchased, what is the amount that has been spent, what is the region, all the other demographics, names, and everything. So there could be like 10, 20 columns, right? Now, what we are interested in is we are trying to understand the revenue generated in each of the country or a particular country. So first, as for example, that you have this customer ID, right? You have the orders, right? So the amount that is being spent on the order and the country where this is spent. So what I'm trying to understand here is like Amazon is in many countries, right, all over the world. So let's say we have data in India, we have data US, Europe, and so many other countries. So let's say we have, for simplicity, we have around 30 countries, and each country has probably 10 million records. Okay, 10 million records. So now what we want to do is we want to understand how much of money or how much of money is being made in India across all customers. Okay, so basically what we are trying to do is we are trying to get how much of money is being made in India. Okay, so that is the requirement that we are trying to accomplish. Okay, now what we could do here is like again, there are multiple ways how you can achieve it, but for simplicity, let's say somebody, a new engineer has come and this person has written a code something like this, where okay, hey, I'm going to do first there are like 10 countries, right? So I'm going to do sum of amount, group by country. Okay. And once this operation is done, what I'm going to do is I'm going to write a where clause to actually remove, to get only the details related to India. Now, this will give me the data that I require. But there is a problem with this approach, right? So, what you are doing is like you are actually putting an operation on 10 countries, which and then you are basically filtering out. We don't need the operation to be done on the 10 countries, right? We don't want to know the revenue generated for all the 10 countries. We are only interested in knowing the revenue that is generated in one country, right? Which is basically the our final output here we are receiving. But why do we have to do the sum for all the countries? So instead what we could do is second approach, what we could do is we could first basically do a filter where we say, hey, first, let me just get only the data that is required, right? So I only want the data related to India, and then I will do a sum, okay? Sum of the revenue. Sorry, sum of the amount. This way, what I am avoiding here is I'm avoiding doing an aggregation on 9 other countries. Okay, so I'm only doing aggregation on one country which is required for me. Okay, so these are the two approaches, right? Now, obviously, the second approach saves us time, right? This is a better approach than the first approach. So imagine that this new engineer has actually put this approach. Now, will Spark execute this as it is, right? So now this is where the Catalyst Optimizer comes into the picture. So the Catalyst Optimizer will scan the code. It will basically create a logical plan out of this. Okay, so it is not going to execute as it is. It is going to create a logical plan out of this. Now, logical plan, the optimized logical plan it will create. So once this optimized logical plan is created, it will create a physical plan, and then this physical plan is what gets executed. Okay, now this plan may be different than what the engineer would have written, right? So in the engineer would have written like, okay, first I'm going to do an aggregate, and then I'm going to do a filter, right? But this plan may say, hey, first we need to do a filter and then we need to do aggregate. So this way, your performance will be improved, right? So that is the concept of Catalyst Optimizer. Catalyst Optimizer does this, right? And in the definition, we have seen like, Catalyst Optimizer does this by using certain rules, blah, 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 right? So obviously there needs to be some rules for the Catalyst Optimizer to take some decisions, right? So there are certain things, okay, what Catalyst Optimizer does. Okay, so how does this optimizes the query? So there are certain rules that the Catalyst Optimizer uses. So some of them, like it has something called as predicate pushed on. So what does predicate pushed on mean? So predicate pushed on basically tells you that we need to use the filter before it joins. So this is basically where before join. So if there is join and if there is a where clause that needs to be done, then what Catalog Optimizer says, like first let's filter out all the records. First put the where clause so that we reduce the number of records that needs to go into the join, right? So that is one of the rule. And second is we have something called as column pruning. Okay, so imagine there are like 100 columns, but do we really need all the columns, right? only the columns which are required, though only those columns will be read. Even if you have like 100 columns, if you're only using two columns, like in our example, we only need the amount column, we only need the country column. So even if we have like 100 columns, we don't need all the other columns. We only take the columns which is required. So those are the columns which we will take. Okay. Join reordering. So there's another rule like join reordering. Like if you have a small table, this would be the smallest, and you have a big table. You always look at the small table first, right? That is one of the rules that the Catalyst optimizer uses. There is a broadcast join. Okay, so a broadcast join basically like if you have a smaller table, instead of sending the table again and again, what we will do is we basically kind of share that table like a cache, right? So that is basically broadcast. So if the table length is like less than 10 MB, then broadcast join will take it. Then uh, projection push down. So basically avoid unused columns. So these are basically the rules that the Catalyst optimizer uses to kind of ensure that the right approach is being followed. Okay, so let's take an example. So we have the code here. Okay, so we have the code here written. So what we are trying to understand here is like we have the customer data. So this is a very, very small data. We just have four records of the same concept that we talked about. The customer data, we have the IDs, the names, and which country they belong to, the orders. Then there's another data frame called as orders, which is linked to the customer ID. So these are the orders that we have and the amount that is spent, right? So this is a data frame. So we are creating the temporary views for both customers and orders. We are writing a Spark SQL where we are joining the customer ID with the customers with the orders, and we are only trying to get the US records here, right? So this is a query that we have. What we are trying to do is we showing the results, and then we are actually showing the execution plan for this. Okay, so let me just go ahead and execute this. Let's execute this here. The code is getting executed, so let's just give it a few seconds. All right. Okay, so we do have the results here. So we have the total for the US clients, US customers. This is the output that we have, but we are more interested in the plan, right? So the logical plan that the Catalyst optimizer has used. Now look very closely, right? The first thing that we have join, we have filter, correct? So if you look at here, right? So we have a join, we have filter. So join actually we have put join first and then we have put filter. But look at how the logical plan is. The logic plan is like first we will do the filter and then we will do the join. So that is the optimized version. So even though we said like we are joining and then there's a join first and then there's a country the filter, but what is happening in the Catalyst optimizer is that the filter is applied first, so only the required results has been taken, and then the join is happening, right? So again, that is a logical plan. So once the logical plan is done, right, so it will analyze the logical plan and come up with the right or optimized version of this join, right? So you can see the details like, the filter is applied on the country code, which is 9. The inner join, the joins are all applied, and then the optimized logical plan is here, and then it gets converted into a physical plan. It's basically whatever, we have the broadcast join, we applied the filter and all those things. So all these things is taken care by the capital optimizer, and then finally we will get the output, right? So this is how the catalyst optimizer works. So even if we come up with a query which is not really optimized, the catalyst optimizer will look at the query, it will scan the query, it will convert it into logical plan, it will analyze it, it will ensure that it will uses the right rules to kind of uh, optimize that query, convert that logical plan into physical plan, and then execute it. That way, we will have a better version of what we have written. So that is the Spark's internal capability that we have. So this is an important question, as I mentioned. So I hope this was clear to you guys, and I'll see you guys again in my next class. Okay. What are coalesce and repartitioning, and what is the difference between them? So another very important interview question. So you should know what is coalesce and repartition. But before understanding what is coalesce and repartition, let's understand what is actually a partition, right? So if you need to understand this coalesce and repartition, you need to understand what exactly is a partition. So we have a data frame, right? So let's say we have a data frame, the data is there. Now what happens is we can split this data frame into certain partitions. So let's say we have 100 million records. So you can split it into 10 partitions. Each one might be like 10 million records, right? And so each partition will have one executor. So why this is important? So if you have more partitions, right? So here in this case, we have 10 partitions, which basically means there is more parallelism. Parallelly, there are like 10 executors that runs, right? Fewer partitions, but at the same time, like what happens with fewer partitions, you will have fewer parallelism, but there will be less shuffle, right? So you might have to kind of shuffle the data into the different nodes for the partitions to take effect, because you might a partition, let's say you partition based on country, so you need to get all the data related to country into one particular node, right? So there will be shuffling. So this is the overhead that happens here. So basic concept, right? Now coming back to the coalesce and repartitioning, right? So now we talked about the partition, right? So you can increase the partitions, you can decrease the partitions. So both both repartition and the coalesce function, they help in adjusting the partition. Okay, so that is what both of them does. So what repartitioning does is it it has the flexibility to increase or decrease the partitions. Okay, so there will be full shuffle that happens, but this basically has the capability where you can increase or decrease the partitions. So you might have like 10 partitions and you might want to increase the partitions, you can increase it. At the same time, you might see like 10 partitions, that's way too many. You want to decrease this using repartition, you can decrease the partition, right? So that is what the repartition does, and it involves full shuffle. Okay, that is an important point. Coalesce, on the other hand, is only used for reducing the partition. So if you want to reduce the partitions, coalesce is the one that you will be using with minimum or no shuffle, right? So this is again an important concept or important point that this happens with minimum or no shuffle. Okay. Now if I look at certain features, right? So with partition, repartitioning, and the coalesce, so shuffling, yes, repartition, as we seen the definition, it does the shuffling. So there will be shuffling involved. Increase the partitions, yes, you can increase the partitions. You can also decrease the partitions. So the performance would be a little bit slower, right? Because you will actually have the full shuffle, right? So we talked about the full shuffle. So compared to the partitions, the performance will be lesser. So if you want to just balance the data, so this is a use case. If you want to have a balanced data, this is what you can use for repartition. Now look at coalesce. By default, there won't be any shuffle, but yes, there will be a little bit of shuffle, but comparatively to repartitioning, coalesce will not have. Can you increase the partitions? No, you cannot increase the partitions. You can only decrease the partitions, right? Performance wise, it's much faster than the repartitioning because it has minimum or no shuffle. So that's where the performance gets into the picture, right? And what is the use case with it? So if you want to merge output file. So let's say you have like you are reducing the partitions, right? And you want to merge those. Let's say from 10 partitions, you have come to three partitions. So all those 10 files now has to be merged into three files, right? So that's the use case that we can have with this repartitioning, sorry, coalesce. All right. Now, let's look at an example as well. Like for example, let's take a scenario. Okay, so before we go to the code or an example, let's take up a simple use case, right? So let's say that you have a huge Parquet file. Okay. Now, this could be any file. I'm just taking an example of a Parquet file, and it has 10 TB data, which is very big, right? And obviously, when you have a bigger data, we need to partition it. So let's say we did 50, let's take 500, okay? So we have like 500 partitions, okay? This 10 dB is, we have partitioned into 500 different partitions, okay? Now, we have done all the filtering and everything. So we have the filtering and everything which is done, and we are left with 5 GB of data, which is very less, right, compared to the 10 GB. Okay. Now, how do you want to write this file? So you have a 10 TB input file, which has, we have 500 partitions, and now you have only 5 GB as the output. Okay. Now, if you keep this as it is, right, 500 partitions, so this 5 GB will get into 500 different files, right? Because that's the number of partitions that we have, okay, which is not good because 500 small files, you will have too many files, and your performance will be, HDFS performance will degrade. Okay, this is not a good practice. You should not have too many small files. So this is where we can do this. We can reduce the number of files, right? So what we can do here is instead of 500 partitions, so let's say the data frame is DF, what we can do is we can use coalesce. Can use coalesce, and we can specify the number of partitions that we want, number of files that we want, and then we can write it back to Parquet. Okay, so this is basically a use case that we have. So we have five, instead of 500 files, we are merging those output files into 10 files by reducing the partitions using coalesce, right? So that is a use case. It's a real world use case that we can have. Okay, now let me also add another question to this. Okay, now this is fine, right? But let's say, what if the data is skewed? Okay, so some of these partitions can be very huge, some of the partitions can be minimum, right? Now, in that case, what we could do is we could use a repartitioning. Okay, so we could say repartition of 10. So what it will do is it will basically shuffle the data so that the data is evenly distributed. Okay, again, this is another use case that we can use. Okay, so now let's understand this. I hope this is, the concept is clear, the use case where we are going to use is clear. So now we'll jump into Eclipse and we will look at the code. Okay, again, a very simple code that I have written. You're reading all the Spark context, Spark sessions and everything. So we have an RTD created. So we have the data here. We have an RDD where this is RDD, and then what we are doing is we are applying a coalesce. So basically, we are reducing the number of partitions. So initially, we started with 4 partitions. of number 1 to 100, but then we are reducing the number of partitions here to 2. Okay. And then what we are doing is we are increasing the partitions to 8. So this is basically the code is basically what I'm trying to show is how you are writing the code, how you can utilize the coalesce and partitions. Very simple. You just have to say dot coalesce and give the number of partitions, dot repartition, and just give the number of partitions that you want to use, right? We talked about we talked about the use case when you have to use the repartitioning, when you have to use the coalesce. This is simple execution of the coalesce. So you can see here is the number of partitions changed from 4 to 2, 4 to 8. So a simple concept. Code-wise is all fine, right? So it's a very, very simple change. But the main thing comes where you want to use it, right? You cannot just go and of course you can go and just do a dot repartition coalesce or repartitioning, but please check the use case. When do you have to use the repartitioning? When you have to use a coalesce? This can cause a lot of issues if not used properly, right? I'm talking in terms of performance. Okay, so use this effectively, right? And we talked about the use case as well. So if this is a real use case as well. So when you have this use case, you could use coalesce or repartitioning based on the type. Okay. All right. That is all I have for this use case, and I'll see you guys next session. What are accumulators in Spark? So another important interview question. So accumulators is a shared variable used for aggregating values across all Spark executors back to the driver. All right. So a simple definition. So in simple words, accumulator basically accumulates. So it is accumulators are used to collect metrics from a distributed data. So you have this cluster, right, where you will have different nodes that are running and everything. So what accumulators does is it's mainly used to collect the metrics. So they are certain use cases why we use the accumulators. We have if they we want to count the number of errors that we have. Okay, so like there are 10 nodes, we wanted to just basically count the number of errors across all 10 nodes. You can use accumulators for this. If you want to count the number of bad records that we have, number of filtered records we have, is basically, if you want to monitor the ETL pipeline, right? So this is where the accumulators are used. So this is not for business. So this is an important thing. This is accumulators are not meant for business data. So you don't want to write a business logic using accumulators. So these are basically metrics. So what happens is like in Spark, right? Each task runs its own JVM, Java Virtual Machines, and variables are basically copied to each of the executors. So normal variables, whatever you define, they cannot be updated globally. When I say globally, across the cluster. So this is where accumulators are used, where accumulators is a global variable that basically accumulates the data from across all the nodes and gives it back to the driver. Okay. Now, now let's look at one use case, right? We can have a use case. What is the use case that we can have? Okay. So assume that you are running a bank transactions. Okay. So in the bank transaction, it runs in the cluster, right? And this bank transaction, you want to know how many records are invalid, right? How many records are processed successfully. So basically, success and failure, right? So how many records are invalid, how many records have successfully processed. But you don't want to store this in your internal HDFS, so you want to use an accumulator for that. So this is where we could use these accumulators to kind of accumulate count how many records have failed, how many records have succeeded. So so One other important thing that we need to understand is, so accumulators, when you are using accumulators, right, always use inside an action. Okay, so always use inside an action. Okay, do not use inside a transformation. Okay, so why this is because Spark, see, there might be some issue when you are running a program, Spark program, there can be some issues, right? So in that case, what Spark will do is Spark will retry certain actions. It can retry the task. Okay. So when it retries the tasks are re-executed. So if they are re-executed, then accumulators can get re-executed again. So it can multiply. So that is where it's always important that you use the accumulator in a in an action, not a transformation. So if you have something called as map, filter, do not use these accumulators here. So always use accumulators in actions like for each. So this is where we basically use for each, count or collect. So action. So this is a very important thing that you need to keep in mind before using accumulators. Okay. So there are different types of accumulators. So there's something called as long accumulator. So long accumulator, for you can count the number of rows using long accumulator. So you can have a double accumulator. You can use double accumulator to sum the values. You can use a custom accumulator for tracking complex objects. So again, different use cases, different types of accumulators that we can use. So now let's look at the code. I've written a simple code here for us to understand accumulators. So let me just run this code first so that while we go through the code, right? So this gets executed. So what I'm trying to do here is I'm using a long accumulator to actually count the number of bad records that we have. So this is an example. This is a data. So we have some log information. So there is time here. There is an ID, the name of the user that we have, and some other value. Okay. So there is some bad data here. So basically, this is one bad data where we are saying that there is a missing timestamp. Right. So here it's null. So here we have a missing user ID, and then you have an invalid response code. Okay. So the end we have like 200, 400 response code, and 800 is an invalid response code. So this is the data that we are sending. And what we are trying to identify is we are trying to identify how many bad records are there. So in this example, this is a bad record. This is a bad record. This is a bad record. So there are like three bad records in this data. Okay. Now we are doing some we have a function where we are trying to validate, because you need to tell what is a bad record, right? Accumulator is only for counting, so you need to have that logic in place where we are saying, hey, uh, this is a logic, and if it does not come under this logic, this is a bad record. So we're splitting the fields by comma. A timestamp takes the first field of 0, user ID is the second field, response code is the third field get, and then we are also trying to check if there are any critical fields that are missing. Like for example, if the timestamp is null, or the user ID is empty, or the response code is less than 100, or response code is greater than 599. Some basic logic that we have put, we are basically incrementing. So we are just adding it, right? So, and then what we are doing is like we're passing this to that function, and then we are printing it, right? And then we are seeing like what is the total number of records. So bad records accumulated dot value, and then we are printing it. So that is what we get. Like the total number of bad records is 3, right? So this is what the accumulator does, right? So let me just pull it down a little bit, and let me just go back to the code again. Simple code, what we have, we are using a long accumulator because we want to count the number of bad records. This is a sample log data that we are passing. We have a function that we are using to validate the log entry. Here I'm just checking if timestamp is null or user ID is empty or response code is within a certain value. And then if that is the case, then what I'm doing is bad accumulator dot add. So I'm just adding one entry here. So this is a bad accumulator, bad record accumulator that we have defined here. I'm just adding one record to that. And finally, I'm basically printing all that record here, which is basically 3. So this is what accumulator does. All right. So that's all I have this session. I hope you guys understood this, and I'll see you guys in my next session. Okay. What are the deployment modes in Spark? So very important question. It's a sure interview questions in most cases. Okay. So what are the deployment modes in Spark? Okay. So first, let's understand what does it actually mean. So you write a Spark application, right? So you write a Spark program. So you need to run the Spark job, right? So where you run the Spark job matters, right? So you can run this. So that is what it's a deployment mode. Is where you are deploying. So you can deploy this in the client mode. You can also deploy it in the cluster mode. Okay. So these are the two important two modes that you can deploy your code. Okay. Now, why this is very important? Because once you deploy it, it builds the DAX, it talks to the yarn, it schedules all the tasks, collects all that information. Basically, your entire job runs, right? So when to use a client mode, when to use a cluster mode. But before even when to use each of these, what exactly is a client mode? What exactly is a cluster mode? So you have a cluster. So a cluster can have many different nodes, right? So let's say these are different nodes within that cluster, and you develop the code in your local system, which is basically you're writing the code in laptop. So you have all the code written here, and if you want to execute, you can execute this code here in the laptop, right? So which is your local machine. So that mode is called as a client mode because you're executing the code on your laptop. But if you want to if you execute this code in the cluster in one of the nodes here in the cluster, then it will become a cluster mode. So that's the basic difference. If you're executing this code in your machine, that will become a client mode. And if you're executing this in the cluster, in one of the cluster machine, it will become a cluster mode. Okay. Now, important to understand, right? Where we need to use a cluster, where you need to use a client mode. Okay. So what happens in the client mode? So you are running in your local machine, right? Here you are running in the cluster machine. As a user, you have to monitor because if it's your own laptop, other people will not have access to the laptop. And obviously the network dependency is high because if you get disconnected, if your Wi-Fi or anything gets disconnected, it's not good. So when it is useful when you want to develop. Okay. So let me just make a note here so that we are clear on all the features that we just talked. So let's say this is a feature, this is client mode, and this is sorry, this is cluster mode. So we're talking about the driver where it runs. A driver is basically the program that is running, right? So client mode is in your local system, which is machine, and this runs in the cluster, one of the nodes in the cluster. So monitoring, you have to monitor it, the user. Here it gets monitored using yarn, right? Network dependency is there. Yes, there is high network dependency. Here it's low dependency. So use case, right? So when you develop a code in the development, right? So you can use this mode. So you would and also you will use for debugging. So let's say you are writing the code for the first time, right? If you are writing the code, you need to test it and everything. So in the development, you use your local machine, develop it, test it, debug it, and then you push it to the client. And if you are running in production, you cannot rely on your system, right? Because other people may also use obviously they will use. So that is where you will have to use a cluster mode. Okay. And important thing is like when you're doing a Spark Submit, right? Spark Submit is basically where you are submitting a job. When you are doing Smart Submit, your laptop should be alive because if you close the laptop, the Spark Submit, everything goes off, right? So you need to be alive. In production, you can disconnect your laptop because it runs in one of the cluster. Cluster is always running, right? Again, cluster keeps running. So if somebody cluster, then it's a different scenario. But otherwise, your cluster will keep running. So it will run in one of the. So in simple sentence, right? For development, right? You're developing something, you're debugging something. You can use the client mode, but for production, that has to be a cluster mode. So this is the basic thing, right? All right. So that's all you need to understand where you to use the cluster mode, where you need to use for production, cluster mode, for development or debugging, use the client mode, right? Okay. That is all I have, and I'll see you guys in my next session. Okay. So performance tuning, right? Sparks performance tuning. This is one question, regardless of your experience, you will be asked this question. So, what are the performance tuning techniques that you have done, or what are the performance techniques that you are aware of? Okay, so we need expect these questions, guys, all the time. Okay, so basically, performance tuning, right? So, before we get into details of the different techniques in the performance tunings, we need to understand why the jobs become slow, why the performance degrades, right? So you need to understand that first. Okay, so there are different the reasons why the Spark performance will degrade. So if there is too much of data movement, right? So too much of data movement, basically data shuffling, correct? So why this is like, if you have data shuffling, you need to move this data from one place to one other, so that input output operations happens, that will cost us, right? So that is why it is one of those reasons why we end up having a performance issue. Okay. And poor memory usage. So if you have memory, if you're not utilizing it, or if you're overutilizing it, again we'll see that, then you will end up with the performance issues. So let's say you have like memory and you're using 99% of the memory into one operations, then the other operations will slow down, right? Bad partitioning. So bad partitioning would be like if you have too many partitioning or too little partitioning, then that will also be a cause for your performance degrade. Like for example, if you are having like a 100 partitions and each partition is like 2 MB or 3 MB, so you are basically generating too many small files in HDFS, which is not a good thing. That will cause a performance issue. And if you are using a wrong join, right, the wrong strategy, so you have different joint strategies here. If you're using some wrong joint strategy, like if you're not using broadcast where you're supposed to use broadcast, and those things can also come up into the performance issue. And of course, and another important thing is inefficient file formats. Okay, so if it is very important for you to choose the right file format. If you're not choosing the right format, then that will also cause the performance issue. So what can be done to actually avoid these performance issues, right? So we need to understand, we have understood the cause, right? So what causes the performance issue? So what should be our goal in order to increase the performance? So we should reduce the input output operations. That means reading and writing less data from the disk, right? Less reading and write from the disk. So this will ensure that the performance is not degraded. So this is reduce. Okay. Uh, Shuffling, of course, you need to reduce the shuffling, the data movement from one node to another. You need to reduce the shuffling. Memory usage also you need to reduce. So if you don't use the 100% of the memory, you always need to put some sort of memory here is to ensure that we avoid the memory spills or out of memory errors. So you will see this out of memory error issues happening in the production environment, all the stuff. So you need to reduce that. You need to ensure that you increase the parallelism, but effectively. So do not use as many nodes, as much of parallelism as you want. So again, use the CPUs efficiently, right? So that is an important thing. Recomputation. So you need to reduce the recomputation. So how you can reduce the recomputation? So you could use coalesce, you could use repartitioning, you could basically cache the data, right? So these are some of the things that you could use to kind of like reduce the, increase the performance. Okay. Now let's look at some ways how you can. These are basically the goals, right? Now let's look at the each of this in detail. Okay, so the right file format. Okay, so we need to use the right file format. So why it matters? So Spark is fast when we are working with the columnar storage formats. So if you have a columnar storage format, then Spark performance will be very fast. So if you're using something like CSV, the performance will be very slow. Uh, if you're using JSON, it will be slow. If you're using something like Spark or ORC, your performance will be very fast. So a lot of times we end up using the Parquet. Again, there might be scenarios where you have to use the JSON if the data is coming in that format. That is fine. But unless if you have a choice, always prefer to go with a columnar storage, either Parquet or ORC. So this reduces the input output disk, network traffic, memory usage, and it also, this is a column based storage, right? So it has that built-in compression, and if a predicate push on, it reads all the required columns only. So these are some of the advantage that you have if you are using the columnar storage, which is RK or ORC, right? So next, memory tuning, right? So we talked about one of the goals, right? We need to have right memory tuning. So Spark uses memory for different cases, like for caching the data, for shuffling, aggregations, joins, right? So for all these things, Spark uses the memory. Okay, so you need to configure your nodes executors. So there are certain configurations that you need to do. Spark dot executor dot memory. This is one. Then there is Spark dot executor dot memory overhead. So these are some of the configurations that you need to do. Spark.driver.memory. So you need to have the optimum configurations here. So proper memory tuning, right? So this will avoid out of memory errors, disk spills, and execution speed will be improved. So typically these are something which is already set up in your production environment. You don't have to worry about it. So this is like trial and tested mirror depending upon your cluster size and everything. So this memory tunings can be done. So mostly you don't have to do it. Again, there are certain cases where the developers have to do it, but otherwise it's something, if you have a production team ready, they will take care of that. But you need to know the concept here. Okay, you should be using cache and persist because when the same data set is being used again and again, you need to cache it. So you will have to use the cache and persist to ensure that you are storing this data in memory and you are not recomputing it, right? So one of the things that we saw, like recomputing takes a lot of time, right? So because you're doing the same thing again and again. So once you have already done it, just cache it so that that is available. You don't have to recompute it. So you don't have to reread it from the disk. You don't have to recompute it. So you already done it. You just utilize it. Okay. So that's one thing. Then we also have something called as coalesce and repartitioning. Again, we talked about the efficient utilization of partitions, right? So you need to ensure that you have right amount of partitions. So why? Because if the partitions are sized badly, then it will be cause an issue. Like if you have too many partitions, right? If you have too many partitions, then it's a overhead. At the same time, if you have too little partitions, then most of if your most of your nodes or your CPU are actually sitting idle. That is also not good. So again, you need to ensure that you use coalesce and repartitioning to optimize the partition. So use the repartitioning if you want to rebalance the data using shuffle. Use a coalesce if you want to merge partitions without shuffle. Like if you have too many files, too many small files, then you can use coalesce to kind of merge them into smaller into less files so that the performance will be improved. So repartitioning, as I mentioned, for load balancing, coalesce for reducing the output files. Okay. And of course, we need to also ensure that you use the right join. So that join optimization is another important thing that we need to do. What join, what is the right strategy, right? That is also matters. So you need to use the if broadcast join is a possibility, please use that broadcast join. So this will avoid the shuffling, the network transfer, all these things. Then, if possible, you also have to use the serialized data. So, serialized data, Spark sends data between driver and executors, right? So, using efficient serialization, it reduces the memory footprint, it speeds up the network. So, the serialized data moves much faster than an unserialized data. So, there are different serialized data, like, for example, Cairo serialization, right? So, this is a very efficient and fast the serialization. Okay, so uh, that is one approach that you can take. Partitioning. Again, we talked about partitioning, right? So good partitioning. Make sure all the CPUs are busy, right? So these are some of the things that you can try to ensure that you are using sorry you're using the right techniques and everything. One very basic thing is the filtering, right? So if this is one important concept, you need to filter as close to the source as possible. So let's say you have a lot of records, let's say 1 TB records, and you want to do some processing on it. Now the question that you should ask is like, do I have to do the processing on all the 1 TB data records? Or are there some records which can be filtered? If there are, for example, this 1 TB data might contain data related to US and India, and you only wanted to do your process on US data. So instead of doing the instead of doing all the computation for both US and India and then filter it, you need to kind of first filter it. So do the filtering as close as possible so that you are eliminating all the records that you don't have to actually reprocess or recompute or compute, right? So that is one basic thing, and it is same for any technology, whatever, if you're using SQL, Informatica, whatever it is, ensure that you filter it as close to the source as possible. So these are the basics, or these are the some of the techniques that you can use to kind of uh, improve the performance. So very important to first understand why the performance degrades, what causes the performance, and then based on it, you have different ways how you can improve the performance. All right. So that's all here, and I'll see you guys again in my next session. Out of memory. So, what is out of memory? And have you faced an out of memory issue? So, this is how the interview question will be. Okay. So, what is out of memory? First, let's understand what is out of memory. The out of memory happens when executors or the driver try to hold more data in memory than available in the JVM. So, usually due to large reshuffles, joins, queue data, or excessive caching. So, this is what out of memory is. So, in simple terms, what is happening is, so let's say you have 100 MB of memory, and you're trying to load the data which is like 120 MB of memory, right? So you only have 100 MB memory, but you're trying to load 120 MB of memory. So that's where the memory overflow out of memory happens. It basically says, hey, I don't have enough memory here. So that is what out of memory means. Okay. So what happens when you have a out of memory? So your executors crashes, there will be job failures, there will be task retries, and there will be extremely slow performance, right? Because you need some memory to kind of do certain tasks, right? So that's what happens. So out of memory can happen on your executors. They can happen on your driver programs, or they can happen during a shuffle. They can happen during caching. They can happen during joins. They can happen during aggregations. So there are places where you can have this out of memory issues. All right. So now, why out of memory happens, we have seen, right? So let's look at a little bit in detail, right? So there is like too much of data in memory, right? And what could be an example, right? So if you are caching large data sets, okay, now large data sets. So every time you cache the data set, so let's say you have 1 GB of memory and if you're caching 700 MB of data. So that means out of 1 GB of memory, you've already used 700 MB of memory, and then you are only left with 300 MB for all your operations, like reading the data, writing the data, performing joins, all that stuff, right? So that will cause a performance degrade. So this is one important thing you need to always remember, like what is the memory that you have and what is the memory you are trying to cache, right? Uh, Large shuffles. Again, shuffling is movement of data from one mode to another. If you do large shuffling, then obviously that will also cause a lot of issues, right? So some of the examples of shuffling, like if you do a group by, a join, distinct, right? So these are some of the operations where you have shuffling. Then if there is skewed data, so one of the partition can be very big, the remaining partitions can be small. That also cause issues with the memory. Obviously, if you have a wrong partition size, like if you have too few partitions, so two very little partition basically causes a lot of little files, right? So that will also cause memory issues if you are doing the wrong partition size, that is right. Um, Wrong partition size. And again, broadcasting. So broadcasting large variables, sorry, broadcasting large tables, similar to the caching of large data sets. If you are, it's very similar, right? If you are if you are broadcasting large tables, basically you are putting a lot of memory already used, right? So, and of course, executors, you need to provide a proper memory. So if you do not have the proper memory or insufficient memory, then that will also cause issues. Serialized objects as well, like if you have objects are very large, that will also cause an issue. Okay. So these are some of the things that can happen when out of memory can happen because of this. And it can happen anywhere, like in joins, aggregation, shuffle, caching, all this stuff. Okay. So now there are different types of OM errors that you will encounter. So the most common is Java heap space. So this is a very common thing that you will encounter. So it basically since the Java virtual machine heap size it's exhausted, right? Then you will have something called as out of memory error, a meta space, like too many classes, all these things. So overhead limit exceeded. These are all the out of memory errors that you will encounter. So what you need to kind of ensure that this is something that happens. Even if it happens, you can kind of debug and try to see like why, where it is happening, and take steps accordingly. But it's always better to kind of ensure that you follow proper structure, uh, the shuffling, whatever that we talked about, the shuffling or the partitions, have the right partitions and everything. So it's always better to kind of prevent this than to actually solve, because this can be very big headache for us to solve the out of memory issues. So how do we prevent, right, the out of memory issues, right? So we need to ensure that we have sufficient memory. That's the main thing, right? So one thing is, like, there are two ways. If you have a less memory than what you need to increase the memory. So let's say if I have 100 MB of memory, but my process takes like 200 MB of memory. So this is not sufficient. No matter what optimizations I do, this is not really sufficient. So I need to increase my memory. That is one thing. And if I have sufficient memory, right? If I have 500 MB and all the process takes 200 MB, I need to ensure that my process are optimized. So I do not want to create unnecessary shuffles, or I don't want to create unnecessary partitions so that this memory gets increased to 300 or 400. So those are two things at the code side, that you there are few things that you need to do at the code side. At the infrastructure side also, there are few things that you need to do, right? So let's talk about the infrastructure, because we talked about the code in other videos as well. So you need to you need to increase the memory, like you need to increase the spark.executor.memory. So these are the configurations that you need to ensure you increase. So there is this will increase the executor memory. You also need to do memory overhead, spark.executor.memory overhead. You also need to increase the Spark dot driver memory as well. So this is driver dot memory. So you have to increase this. So these are at the some of the things that you can take care to kind of ensure that the out of memory does not happen. Or if it happens, then these are the steps that we need to do, right? Okay. Uh, Huge partitions. Use partitions efficiently. Do not use very less partition, because it will cause a lot of smaller files. Use your partitions effectively. Shuffling, reduce shuffling as much as possible. So again, shuffling are inevitable, but within the code, right? Ensure that, if, for example, uh, if you're using join, and if there is a possibility for you to kind of use a broadcast join, please use a broadcast join, so that you don't have to shuffle the data between multiple nodes. So that's one example. Like distinct is another example. Like sometimes the data that we get is not, we don't have that duplicates, and you don't have to use the distinct. So often I see people just, that is one of the default thing that you do. Hey, select distinct, that blah blah blah. But you don't really need to use a distinct. You need to first check if you actually have the duplicates there. If you do not have the duplicates, do not use the distinct, because it causes performance issues, out of memory sinks and everything, right? So these are things that you can use. Uh, Again, if you have a skew data, like one of the partitions is having more data, the other partition is having less data, those are the things that you need to also take into consideration. So um, use cache carefully, right? So again, we are dealing with memory. So if you have a very large data set, it is always advisable not to cache it unless you have a lot of data, lot of memory available. So very large data set, do not go for caching only. And and also, if you are using the data once, like you created a data frame and you are reading the data frame and you're using it only once, do not cache it. You don't have to cache it. Just because cache is there, you don't use it, right? So there are oftentimes when I review the code, I see sometimes like people just use caching just like that, because they think that at some point they will use it, but they don't use it, and they don't go back and remove this code. So that is one thing that you need to ensure, that if you are using the cache, right? And if you're using the cache, ensure that the cache, whatever that you are using it, has some value, right? If it is used only once. And also, once you have used cache, ensure that you uncache or unpersist it, because if you have to release that cache, right? So if you have 1,000 lines of code and you're using cache at 10 different places, uh, let's say at 500 line you are using the cache, and then after that you're not using it, right? So it is always better to kind of release that, right? Uh, and also some of the important things like don't do something like this at driver collect. Don't want to get all that information here, right? So you also need to ensure that this is something which is taken care. Okay, so these are some of the things that you can use or take care to avoid, or in some cases, even after doing all these things, you may not be able to avoid, then you will have to go back and kind of change those configurations like the executor memory and all other stuff. Okay, but this is a good list of things that you can do to kind of avoid or work uh, on the on the memory issues, outer memory issues. Very important question. So I hope you were able to understand this, and I'll see you guys in my next class. Hello and welcome to another session in the Spark series. So in this tutorial or in this video, we will look at Spark window function. So these are basically the functions that are used to calculate results such as the rank, the row number, and some other the row number, the dense rank, and the lead lag, something that you might have seen in your SQL databases like Oracle. So the same things we can calculate this here. So what this does is basically it is going to divide or partition the data over a range, and then based on that partition it can apply these functions, the window function, and it can give you the result. So we'll look at some of them here with an example. So we are going to use the same bank transaction data for this. So I'm going to quickly execute this data, and we'll look at the data once first, and then we will see what functions or what window functions that we want to apply on this. So this is the data that we have. Okay, so the first thing that we want to do is, so we want to apply, or we want to let's say partition this data, right? So there are different columns that we can partition. So let's say customer ID. So first we will partition the data based on customer ID, and then we will apply this window functions over there, right? So in order to apply this window function, we will need to import a library. So I will have to say import org dot Apache Spark SQL. We have to say expressions, and from this expressions we have to import windows. All right, okay, so the first thing that we have to do is we have to create a window specification. So this is basically what you want to do, on what partition that you want to create, right? So we want to create a partition, we want to partition data based on customer ID. So so the first thing that we will do is we'll create a window specification. So we'll say window spec, then window dot, we have to say partition by, and what is the column name that we want. So you can see multiple column names, but let's just take the customer ID. So we are basically partitioning on customer ID, and you have to give some order by, so on what you are ordering this. So let's say you can give the same column, but let's take customer account balance, right? So we will take the customer account balance. All right, so this is our window specification, and so let's go ahead and apply some functions, right? Window a function. So this is the data frame, and I'm gonna create a new column, and I'm gonna call it as row num. All right, and I want to apply the row num function. Okay, so what row num does? So row num function will give the sequential row number starting from 1. So here is a customer ID. This is what we partition by. So once you partition based on customer ID, right, so what it will do is it is going to give the row numbers, right? So it is going to give the based on this order by. So the least for the same customer ID, the least customer account balance, because this is basically you're ascending, right, d by default. So the least customer account balance will have the first row number, and then second row number, and so on, right? So the function that we will use here is we have to say row number, right, and dot over, and then here you have to give the window specification. All right, so okay, so we will first execute this. So I will do a simple dot show, right, and first let's execute this first, and then we will see this data. So I am going to, okay, let it be, let me just execute this. All right, so we have this data here. So you can see here the row number, all of them. So we have 1 and 2 here. So let me, okay, let me do one thing. So instead of selecting all the columns, let me just select few columns that are totally required for this. So if we require more columns, we can add it at a later part, but for starters I just want couple of columns here. So one column is obviously is my customer ID and my customer account balance, because both of them are used in my Windows spec, right? Okay, so we'll start with this, and let me execute it. So we will start with this. If more columns are required, we will select from the select using the select transformation or select method. All right, so this way it will be easy for us to understand how this functions, right? Okay, so if you look at this, right, row number, all of them are so most of them are 1. That is because we have only one record here, so there is nothing to partition. But if you scroll here, if you look at this data, so we have two records with the same customer ID, and one is given as 1, second the other is given as 2. That is because your customer account balance, so this has less customer account balance, so it is going to have a row number as 1. This will have a row number 2 because it has more customer or more customer account balance. Similarly, we have one more record where we have the same customer ID, and this looks okay. So this is where the problem is, right? So this is again something that we need to understand. So this is, if you look at this has more, this is basically having more number, but then if you look at the row number that was given, it's basically says this is less than this, which is not the case. Now why is this happening, right? So this file, when if you do a print schema, all of them will be shown as a string. So let me show that. So let me do a print schema here. So if both of them are string, basically it will go by the ASCII word, right? So that is why you are seeing in some conflicts there. So we will need to convert that to an integer. So all of them are string, right? So because all of them are string, so you are ascending and descending are basically happening on the ASCII value of the string. Okay, so we need to convert this, right? So we need to convert this to a data type, maybe a double or long, right? So let's convert this to a double. So here, so I'm going to use the column here. All right, so I will use a call, and here I will use cast, and the data type that I want to use is let me convert this to a double. All right, so if I execute this again, now this time it should treat this particular column data, right? So now if you can now if you see here, right, so we have the data in the right order. Okay, so this here if you see this is 10,000, this is 12,000, and this is where we had the issue, right? So now this is sorted, so we have the data in the proper order. Okay, so moving ahead, so this is what your row number does. All right, so there is one more thing which does similar thing, so which is basically the rank. So what rank also does is it will provide a rank or a number to the result within the window partition, right? So when there are ties, what it will do is it is going to give leave a gap. For example, let's say we have two customer IDs and the account balance is same, then both of them will have the rank as 1, but then there won't be rank 2. The next record will basically be rank 3. So that's what your rank does. There is one more function which is dense rank, which does exactly what rank does, but in case there is a tie, let's say the two customer IDs are same, what it will do is it will give both of them as rank 1, but then the next record will have rank 2, so it will not going to skip that. Okay, so let's apply those as well. So I'll use with column here, and I will call it as rank, and here the rank function, I'll say rank dot over what over the window specs, which is this one. All right, and similarly I can copy this here, and I can give a dense rank, right, and this should be dense rank. So let me execute this. So because we have such a huge data, we may not be seeing this ranks and dense rank value for all of them. So here you can see all of them are basically the dense rank and rank are same. So we are not able to find the difference here. So what I can do is I can let's try a few things. So I can use a where clause, and let me do something where I can say dense rank may be greater than 5. Okay, so some filter conditions, we are applying some random filter conditions, right? So we just wanted to find out if we have certain data where the dense rank or the rank is greater than 5. So obviously that means that you will have at least 5 records with the same customer ID. Okay, so we got some, so we have some data. So let me change this. So what I will do is column of dense rank, and I will see if this column is not equal to. So this is what we have to use, not equal to, and I want to find if there are data where the dense rank and your rank are not same. Okay, so let me save this and execute this. So we are trying to find if there are any columns where any customer IDs where we can spot the difference between your dense rank and your rank. Okay, so we have quite a few of them. So let me pick one of them. So this is, I'll pick this particular customer call ID. So now what I'm going to do is I am going to check, I'm going to change my where condition, or let me just comment this out, and I'm gonna say where column, so this should be equal to this value, and the column that I want to check is customer ID. So I am looking for the customer ID where this is the value. All right, so let me execute this. So these are some of the testing tips that you can do. So if you find a similar situation where you have huge data, but everything looks similar, you don't see any difference in the code, and you want to test them. So this is one of the ways. So try different things where you are expecting different data for different columns. So look, check for the not equal to, bring out this data, identify the unique ID or the custom or the ID that you want to check, and then filter based on this ID, right? So here we have the customer ID. So these are the customer account balance, right? If you look at the row number from 1 to 4, and if you look at the rank, right? So what rank does is, again, you are ordering by customer account balance, so the least customer account balance comes first. But if you look at this, right, so this is rank 1. If you look at the second and third record, both of them are equal, so both of them will have the same rank 2. And because these two have occupied the rank 2, there is no rank 3, so directly we have a rank 4. Suppose if we had 3 records with the same rank, then you will have 3 records with rank 2, then there won't be rank 3 and rank 4, there will just be rank 5, right? So that is what rank is. Dense rank, if you look at this, you have 2 records with the same rank, so both of them are given, but it is not going to skip the next rank. So instead of going to 4, it is going to give you the dense rank, which is the next rank number 3. So that's the basic difference between your rank and your dense rank. If the rank is same, if both of them are same, if there is a tie, dense rank is not going to skip anything, it is going to continue with the next rank. But rank is going to basically skip that number, right, and it will give you the next rank. So that's the basic difference between your rank and your dense rank. All right, now we will use the same customer account number. We'll keep the filter as it is, and then we will try different window functions. Okay, and we'll also do something called as percent rank. So percent rank returns the percentile ranks. Okay, so this is another way of getting the ranks. So it basically returns the percentile rank of rows within a Windows partition. And let me do that. So with column, okay, so let's have this where clause at the end. So I'm gonna say with column, right, and the column name that I want to give is let's say percent rank. Okay, and the everything would be same here. So I'll just copy this here, and instead of dense rank, I will change this to percent rank. All right, okay, and the next window function that I want to do is lag and lead. All right, so what lag function does is it returns the value that is some rows before the current, whatever number you specify, it is going to return the value that is that many rows before the current value. And if you don't find any rows before that, it will give you as a null. Lead, on the other hand, returns a value that is the rows that you give, some rows after the current row, and then it will be null if it is less than the offset. So we will understand this with an example. So let me first quickly write this code, and again I will use a with column way to create a new column here. I will call it as a lag, and this is a little different here. So I will have to use a function called as lag, and I need to specify the column on which I want to add. So I want to use customer ID, and then the second argument I have to pass is number of rows, right? Okay, which will be 1. And of course you have to use this window function, so I'll say over, and this is a window specific. All right, so how lag does this? So basically if you look at this customer ID, right? So if this is a first record, so I have given lag of 1, so this is number of rows is 1. Okay, so basically from here it is basically going to give me a record which is before this. Now there is no record before this, right? So it will give me null. So in this is a current record, so it is going to give me a record before this, which is this record. That is how your lag works. Lead will basically gives me a record in advance, so that is your lead. So you know, let once as will we execute this program, then we will understand, we'll have little more clarity. So for now I'm just going to copy paste here, and I'm going to change this to lead. I'm going to keep it as one column only, the number of rows is 1. So I'm using the lead, and let me execute this first. So once I execute it, once we have this data, it will be easy for me to show you how this lead works, right? We have already seen rank and dense rank, percentile rank also in the similar lines. All right, so let's wait. Let me take this a little bit up. So this is how your percentile rank works, right? So percentile rank basically returns the percentile rank of the row. So and if you look at lag, right, on the customer ID, so we have applied this lag on the customer ID, right? So that's why you're seeing all the same customer ID, we have filtered it. So let's apply this for something else, right? So let me apply this for customer account balance. So this is different, right? So let me apply this for this, and then it will be easy for us to validate. So let me execute this. Let me take this bit up. So we have the schema printed. The next thing is the data. Okay, so so now the data is a little bit better, right? So the first thing is lag. So this is the current record, right? So what lag will print is, from the current record it will go an offset, like the offset here is 1, number of rows, that is your number of rows. So here we are saying from the current record you print the data which is one row before that. So what is one row before this? There's no row, right? That's why you have null. So when you come to the second one, right, second record, now in the second record, what is the account balance before this one row? So before this one row, this is the account balance 6520, that is what you see here. Same, if you go here third record, so this is the current value. What is the value before this? This is the value. If you come here, what is the value before this? This is the value. So that is what you see, that is your lag. Lead is basically returns a value which are before the after the current row, right? For example, if you look at this record, right, what is the date record after this? So this is 16,406, that is what you see here. For this record, what is the data, what is the after this record? So this is the data, so that is what you see. And if you go at the last, this is the current record. What is the record after this? There is no such record, that's why you see null. So that is how your lead and lag work. All right, okay. So other things that we can do with the window function is we can basically do basic aggregations, like you want to do the average, you want to find the average of customer account balance of you, or you want to find the maximum account balance, or you want to find the minimum account balance. You can do that in the windowing function as well. So let's do that. So let's keep this filter condition as it is. So I'm going to say with column, and first I'll find out average. So I'll say average account balance, and I have to use average function, and I have to pass the column customer account balance, right? So let me copy this. I will pass it as customer account balance, and of course you have to say over and give the partition, which is the window spec, right? So we have to give this. Okay, so similarly what I will also do is I will do for maximum, and I'll also do for minimum. So let me quickly copy both of them, and the only change here is the instead of average I'm going to use maximum, rest of them are same. Similarly, instead of average here I am going to use minimum, the rest of the data or the code will be same. So I will save this, and I will execute this. So this way you can also find, you can partition the data based on a column. In our case is this customer ID, and then you can do some aggregations as well for the partition data. So we are trying to find the maximum account balance, we are finding the minimum account balance, we are finding the average account balance as well. So these are the statistics we have: the average account balance, the minimum and maximum account balance, right? So this is about the Windows function. I hope this was clear, and I will see you guys in my next class. Hello and welcome to another session in the Spark series. So in this session we will look at how we can pass set of columns to a data frame. So we are using the same bank transaction data. So what we have here is we have a simple code where we are printing the schema, and then we are selecting few columns here, and then we are printing them or showing them, right? So this is the output here. We have the print schema details. We also have the selected data here. So yeah, so no surprises here. So let me close this. Now let's assume that we have around 50 columns, and then you want to select some 17 or 18 columns, right? So you apply a simple select statement, but after some lines of code, if you want to do some transformations, and you want to display the same set of columns, then again you have to write the simple select column, select the data, and select the same columns, right? And one other thing is the columns, when you select the columns, right, it can be of any order. When you display it, it can be of any order. Some APIs, when you apply, the columns gets ordered in ascending order, and when you apply some other APIs, the column order does not change from the raw data. So if you want to give a specific order to the columns, you can do two things here. First, you can define the columns in a list. So whatever the order that you define in that list, the data will be retrieved in the same order. Now this list, we will have to map it to the data frame. So it will reorder the data frame in the order that is mentioned in the column list, right? Now other advantage with that is you can basically use that list, and if you want to select the same columns, so you can basically pass that list to any data frame, right? So here I'm using one data frame where I'm selecting this column, so I have to mention the column names, right? So if I do some transformations and I have another data frame, and if I want to select the same columns, I'll basically have to copy the same code here. So instead you can basically pass the list, and then it will map it to the data frame, and it will retrieve the data. So this is a very useful feature, and we will also see how we can use this feature to read a fixed width file. So but that is something which is coming up later, but this is a very handy feature to have. So let's go ahead and achieve this, right? So we'll create a list here. So I'll say val list1, and you have to say list, and then here I'm gonna give the set of columns that I wanna get. So maybe I'll just copy the same set of columns here, right? Okay, so let me just comment this out. So I have the list here. Now you can create another data frame here. So let's say valdf1, and I'm going to read this data frame, and I'm gonna say select. Now instead of passing these columns, what I can do is I can basically pass this list. So I'll say list1, and now I have to map this, right? Map this to the data frame. So I'm gonna say map, and this would be column because this I want to be treated as a column, and I will say this. So this means here is a list of columns. I want to map it to this data frame, and this basically means this number of columns or the number of arguments can be any number. So it's not, we are not limiting to 1 or 2, it can be any number, right? Fine. So we have this data map now, and if I do a simple show, so what will happen is this list, it will look at this list, these columns, so it will basically map these columns into this data frame, and if these columns are available in this data frame, it is going to retrieve this data for us, right? And if these columns are not available, then obviously you will see an error. So we will see that scenario as well. First, let me go ahead and execute this, right? So I'm not passing any column names in the select statement here again. So I'm just passing the list. So I have this list. So you can create as many lists as you want, and then you can map it to the data frame, right? So we have this data here. The program is now executed. Now if you look at this, right, the order hasn't changed: customer ID, transaction ID, customer account balance, gender. Now see, this order may change for some APIs but not for all the APIs. Now what happens if you have a column which is not part of this data frame, right? So let me say I will say customer gender 1. So this customer gender 1 is not part of this data frame, right? See, we don't have this customer gender 1, so it will try to map this into this, and if it finds it is not available, it is going to throw an error. So let's execute this, and we'll see what is the error here. So it is also important to understand what how the error, or what is the error that we get. So right, okay, so if you look at this, it says cannot resolve customer gender, and the good part is it will give you the list of input columns, right? It says, hey, you have customer ID, transaction type, customer gender, and transaction ID, transaction date, location, account balance, date of birth. We have transaction amount. We don't have this customer gender, so this is a good indication. So you can basically go and check, oh, these are the columns that are available, so I need to change this column to the one which is available. Save this and execute it, and you can have this data, right? All right, so this is what I wanted to cover in this, a very useful feature here. You can create the list of columns, and then you can pass that list and map it to the data frame, and that will be very useful in certain scenarios. So we'll also see one more scenario in the coming videos where we can use this concept, right? So I hope this session was clear, and I'll see you guys in my next class.